Hello, I'm the Manic Mr. Daycock, and today I'm going to be teaching you how to solve recurrence relations where the complementary function and the particular solution have a term in common. So this is an example that will work out like this, and let's have a look at it. So rearranging, we get un plus 1 is equal to 3 lots of u, that's not rearranging, minus 3un is equal to 1/9 times by 3 to the power of n. Solving the left-hand side equal to 0 for our complementary function, we're going to get something that looks like c times by 3 to the n. On the other hand, solving it with the non-homogeneous part as well for our particular solution, we're going to get something, we want to try something of the form un is equal to d times by 3 to the n. Now, what you should notice here is that this is almost exactly the same function. I mean, it is the same function given that the constant itself is arbitrary. So that means that our general solution at the end, when we add the complementary function and the particular solution together, is going to give us un is equal to c times by 3 to the n plus d times by 3 to the n. Now, how does that work out? Well, in fact, c plus d is just another constant. So I can factor this out and go un is equal to c plus d times by 3 to the n. And c plus d, like I say, is just another constant. We'll call it a. And we get un is equal to a times by 3 to the n. And now, what we can see from this is this looks exactly like just either of the complementary function or particular solution. Obviously here we've got a equals c plus d, but ultimately a is just a number. And this makes one of them redundant, so we're kind of losing a bit of information there. And what we'll find is that this doesn't work. This does not give us enough freedom to always satisfy both, and this is really important, it doesn't give us enough freedom to satisfy the initial condition and the non-homogeneous part. There are two things that need to be solved there, and for that we need two different unknown constants. And so there is a general way that we deal with this situation. And let's go back to the start. So there's a reason I've always been doing the complementary function first. And it's this. If your complementary function is going to share a term with what you want to try as your particular solution, then what you need to do is multiply your particular solution by n so that it is a different function. So in this case, your particular solution that you want to try is going to be un equal to d multiplied by n multiplied by 3 to the n. Notice it is the same function that we would normally want to try, but we're multiplying it by this n here, so that it doesn't look exactly the same as our complementary function. And now from here, we're going to solve in exactly the same way. If un is that, we still need to ask ourselves what's un plus 1? Well, un plus 1 will be d times by n plus 1 times by 3 to the power of n plus 1. Expanding that out, we're going to end up with dn times by 3 to the power of n plus 1 plus n, just d times by 3 to the power of n plus 1. And then remembering that we can deal with this 3 to the power of n plus 1 by writing it as 3 to the n times by 3 to the 1. And factoring out that 3, we get this as 3dn 3 to the n plus 3d 3 to the n. And now we can plug all that into our function at the top here. We're going to end up with un plus 1 is going to be 3dn times by 3 to the n plus 3d times by 3 to the n. subtract 3 lots of dn 3 to the n, and we want that to be equal to 1/9 times by 3 to the n. And now what you should see is why it's vitally important to have this n term. Without it, notice that this term here and this term here cancel completely. And those are the n's that we added. And what that allows is this extra 1 here, this 1, that extra multiple of 3 to the n has survived when otherwise it wouldn't have. And so we end up with 3d times by 3 to the n equaling 1/9 of 3 to the n. And solving for d, we divide by 3 to the n because that's fine, this is entirely positive. We divide by 3 and we get d is equal to 1/27. Okay, now we can go across to our general solution. We have enough information for that. So our general solution is un going to be of the form c times by 3 to the n for our complementary function plus our particular solution, which is 1/27 of n times by 3 to the n. And notice we've still got that n there, that extra n there, so that these two terms are distinct. They are not the same thing. They will not combine into a single constant. Now, trying out, for solving this, we need to now plug in our original condition, which is u1 equals 2/3. So I'm going to put n equals 1, and I get 2/3, because u1 is 2/3, equal to 3c plus 3 to the 1 is 3 times 3 to the 1 is 3 times by the 1 from the n gives us just 3, so minus 3/27, which is 1/9. So we get 2/3 is equal to 3c minus 1/9, which gives us 3c is equal to 5. I'm not sure why I'm subtracting at this point. Plus 3/27 plus 1/9 is equal to 5/9 by subtracting that 1/9, and we end up with c being equal to 5/27. And that gives us our general solution. Finally, at the end, un equals 5/27 lots of 3 to the n plus 1/27 lots of n times by 3 to the n. Or we can simplify it quite nicely. Factoring out the 1/27, we get u to the n is equal to 1/27. And we've got 5 here plus n here. 5 plus n, 3 to the power of n. And that is our final solution to this problem. Okay, going over to one last situation here. Solve the recurrence relation un equals un minus 1 plus 2n minus 3 with u1 equal to 6. So rearrange, we get un minus 1 being equal to 2n minus 3. Now, our complementary function is a little bit more awkward, but we need to remember what is the coefficient here. Well, the coefficient before the un is 1. So our complementary function is going to be something in the form un equal to 1, well, some constant of course, c times by 1 to the power of n. But what is 1 to the power of n? Well, 1 to the power of n is just a constant c. And un equals c is our solution. And this should make sense for the non-homogeneous part, because if I'm solving un is equal to un minus 1, well, what I'm saying is the next term is always equal to the term before. So it's constant. So that makes sense. That makes sense that we should end up with just a constant. Now our particular solution, well, we want that to be equal to, we want to try something in the form of an plus b. But the problem with that is this b is a constant, which means we have a term in common again. And so as always, just like we did before, what I want to do is take the particular solution I want to try, so un equal to an plus b, and then multiply by n. And so what I'm really going to be trying is un equal to an squared plus bn. And now I also need to work out what un minus 1 is. Un minus 1 is going to be equal to a lots of, kind of stuck together there, a lots of n minus 1 squared plus b lots of n minus 1. And we want to expand this out, and we're going to end up with a times by n minus 1 squared. N minus 1 squared, not too difficult to expand. We're going to end up with a n squared minus 2an plus a, because 1 squared is just a. And expanding this, we're going to end up with plus bn minus b. So our un minus 1, oh, one's too big there, is equal to an squared minus 2an. Oh, that doesn't look very nice, does it? An minus a plus bn minus 1. Now, what we want to do is substitute that all in. So we're going to substitute that into our original equation here. We're going to get an squared plus bn. Subtract all of this, because we're substituting all in, so an squared minus 2an minus a plus bn minus b. And we want that to equal 2n minus 3. Now let's see what happens here. Again, notice this term, this x squared term that appeared when we multiply by n, it's just going to cancel out. And that's brilliant. That's actually exactly what we want. We want these things to disappear. Equally, this bn here and this bn here is going to cancel out. And those would have disappeared if we hadn't multiplied by n. That would have left us with nothing to deal with. By multiplying by that extra n term, we are left with this bit and this bit where we wouldn't have been otherwise. So now, let's write that out. Minus 2an is 2an. Minus a is plus a. And minus b is plus b. Although, I've lost another negative sign. That's plus a, that's plus a. So this is minus a. And we need that equal to 2n minus 3. And as always, equating coefficients, we get 2a equals 2. And we get minus a plus b is equal to minus 3. So plugging that in, we get a equals 1. Plugging that into our lower one, we end up with b is equal to negative 2. And so now we can get our general solution, which is going to be our complementary function. So un equal to the complementary function, which is just a constant c, plus our particular solution, which is an squared plus bn. But we now know those values of a and b, so it's going to be c plus 1an squared minus 2n. And then we just need to plug in, as always, our initial condition to work out what the value of that constant is. So we need to plug in n equal to 1, and we get that u1 is 6. So 6 is equal to, that's not 6, 6 is equal to c plus n squared minus 2n. But remembering our n was 1, so 1 squared minus 2 times by 1. So 6 is equal to c minus 1, and so c equals 7. And now we get our final solution of un equal to n squared minus 2n plus 7. Okay, thank you very much. This is an example, 2 examples of what to do when you end up with your particular solution and your complementary function having a term in common. Hopefully you learned something there. Next time we are going to move on to second order recurrence relations, i.e. recurrence relations like the Fibonacci sequence, where you might end up with un plus 2 being equal to 4 lots of un plus 1 minus 3 lots of un. Something like that, where there is 2 different steps from the original un. Okay, thank you very much for watching, and I'll see you in the next video.